Okay, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we are delighted to have Marijn Heule from Carnegie Mellon University tell us about computer-aided mathematics and satisfiability. Marijn is, in my opinion, the world leader in applying automated reasoning to resolving real mathematical conjectures. So this should be a great talk. I'll remind you that besides asking questions, I'll be watching the chat. So I offered you can put questions up on the chat. I will look at them and ask them at an appropriate time in the talk. And of course, there'll be a few minutes at the end of the talk for questions. So with that, take it away, Marijn.
Mike, thanks a lot for the introduction and also for the invitation. I'm very happy to be able to talk here about this topic and you have such an excited series on this new technologies. So I want to begin with just a very short list of the many successes of 40 years in computer-aided mathematics. And probably the first key result has been the four-color theorem. And some decades later, there's also the great result by Tom Hales, the Keller conjecture. And we have seen more and more contributions of automated reasoning in mathematics, whether it's computing God's number or the minimal things you need to solve a Sudoku. But also in recent years, there has been this Erdős discrepancy problem. The Boolean version was first solved using SAT. This was a polymath project, so many mathematicians around the globe worked on this problem. And myself, I've been working on various problems, including the Pythagorean Triples problem, Schur number 5, and more recently, Keller's conjecture. And if you look at the list of the kind of most recent things that have been solved. And so, of course, I picked this list kind of for this purpose, but there have been quite some problems now solved using a satisfiability, or in short, SAT solver. And I think this is very exciting technology for computer-aided mathematics. I'm not sure how many of you already heard of this, but the very short formulation of SAT is, so SAT is short for satisfiability, and ask whether a problem in propositional logic or Boolean formula can be satisfied, whether there exists an assignment that evaluates the formula to true. So the research dates back to the late 50s, early 60s, and in the first, say, 40 years, there was progress, but it was limited. So at the end, say, of the mid-90s, we were able to solve formulas with thousands of variables and thousands of clauses. But kind of in the kind of revolution of SAT, since the invention of a solving paradigm called conflict-driven clause learning, we are now able to solve various formulas from all kinds of applications from industry and academia that have now millions of variables and millions of clauses. I won't be able to talk too much about the SAT techniques. I'm mostly talking about what have been done and what can be done in the future. For anybody who wants to know more, there is the Handbook of Satisfiability. Actually, in February, the second edition came out. That's 1,500 pages on the topic. And also Donald Knuth has although it's officially a subsection of the art of computer programming, but it's also 300 pages on the topic, in which he calls SATs evidently a killer app because it's the key to the solution of so many other problems. One of the reasons why I think SAT has been used for many more applications is that people are looking now at them and they say, okay, maybe I can apply SAT to this problem, or maybe I can use SAT to that problem. But another reason why there has been so much more advances is because the tools have become stronger and stronger and stronger. So we have now 20 years of SAT competitions. And if you look at the winners, so the winners are listed on the right side of the slide. And the plot is showing you the following. So if you look at the benchmarks that we used in the competition of 2020, so the vertical axis showed how many instances were solved if the timeout would have been what is shown on the horizontal axis. And so what you can see, so the strongest solver, say in 2002, was able to solve slightly more than 50 problems in 5,000 seconds. But if you look at the winner of 2020, it was able to solve about the same number of problems in, say, 150 seconds. And it's able to actually solve almost 250 instances. And so you see, and the names are kind of are ordered based on the year of winning. And what you see is almost there is also a chronological order. And it shows every year there has been improvements. And that is also one of the reasons why more and more problems can solved with this technology. In this talk, I want to kind of focus on 3 topics. So first, I want to kind of show some results that have been from the past, although they're quite some of them are recently. Then I want to talk about what makes this, what allows this to work, which is proofs of unsatisfiability. And I want to end with quite a part on what is the future of this technology and what are the challenges and what kind of problems are of interest. So let's first start with one of the problems, and this is Schur's theorem. So we have the following problem. Will any coloring of the positive integers with 2 colors, let's call them red and blue, result in a monochromatic solution of the equation A plus B is C? So on the slide, you see the solutions A plus B is C for A, B, C up till 5. And the answer is yes here. And this is, I can show this with a small example. Without loss of generality, we can assume that 1 is color blue. And if 1 is color blue, if we want to avoid a monochromatic solution, 2 needs to be colored red. And if 2 is colored red, because 2 plus 2 is 4, 4 has to be colored blue. Now, because 1 plus 3 is 4, 3 has to be colored red, because 1 plus 4 is 5, 5 has to be colored red. And if they're both red, then 2 plus 3 is 5 is a monochromatic solution of this. So Schur proposed this problem in 1912, and he solved this problem in 1916. And what he showed is that the thing I showed above is actually holding for any finite number of colors. So for every positive integer k, there exists a number sk, also known as Schur number k, such that the numbers 1 to sk can be colored with k colors while avoiding a monochromatic solution, but this is not possible for 1 to sk plus 1. Schur was also able to show where is this transition, what is the value of sk for 1, 2, and 3. This is what you can easily do by hand. This is actually quite a nice exercise for S is 3. But for S is 4, it's already way more difficult. And Schur, and it actually took 50 years before actually it was determined by Baumert. And it took another 50 years to actually show that Schur number 5 is 160. And not only were we able to solve this problem, but we also generated the proof. And the proof is 2 petabytes in size. So it's enormous. But what I will also talk about later is that actually we can check this with a formally verified checker. Now let's look at another problem, quite a similar problem, but now we're trying to avoid monochromatic solutions for the equation a squared plus b squared is c squared. So on the slide again, you see the solutions up till a, b, and c larger, smaller or equal than 40. And this is very easy to color. Actually, you can even color the solutions up to 1,000 by hand, because there's so much options to kind of do a coloring. So the question is, does the same thing hold? Will any coloring of the positive integers with red and blue result in a monochromatic triple, Pythagorean triple? A couple of years ago, the best known lower bound was a bicoloring by Cooper and Overstreet of the numbers 1 to 7,664. They actually used a SAT solver to do this. Myers actually conjectured in his thesis that you can do this indefinitely. So what we did is we translated this problem into propositional logic such that a SAT solver can deal with it. And in this problem, it's quite easy to do this. So we're going to look for a finite example such that the answer is yes. So we're going to look for the numbers in the range 1 to n. And for every number in that range, we have a Boolean variable xi. And it means that if xi is true, it means I is colored red. If xi is false, I is colored blue. And for every Pythagorean triple, we have two so-called clauses, one stating that at least one of A or B or C is red, and the other one stating that at least one of A or B or C is colored blue. And the result that we have in the 2016 paper is that you can color the numbers 1 to 7,824 using the two colors, but it is not possible for anything larger. In fact, with the right heuristics, we now figured out that you can actually compute the 1 to 7,824 actually within a minute. However, the result for 7,825 took 4 CPU years, but it was 2 days on the cluster TACC in Texas. And if I would have access to the entire cluster, we actually would be able to solve this actually in half an hour. And again, the proof was big, 200 terabyte, but it was validated using a verified checker. And actually, there have been now 4 checkers around that are formally verified, and all of them were able to check the proof. Now let's look at quite some different problem that also excitingly we were able to tackle using satisfiability, and it's the following. So imagine you have the entire 2-dimensional space and you want to tile it with equally sized tiles, square tiles, and you have to do it in such a way that there are no gaps. Is it the case that there's always that 2 adjacent tiles for which they share a fully common edge? So if you think about it, then the only way to tile the 2-dimensional space is to put all the tiles in lanes. You can shift the lanes arbitrarily from each other, but tiles within the same lane, they fully share an edge. And if you go ask the same question in the 3-dimensional case, so the 3-dimensional case is, so we have the 3-dimensional space, all the cubes are of the same size, also no gaps. Is it the case that they fully share a face? And if you think about it, it takes a bit more thinking, but then you kind of also realize that some similar thing happens in the 3-dimensional space. And for example, I just put some cubes there as an example. And for the blue faces, the only way to fully fill it is to have them completely sharing. Heinrich Keller also observed this, and he actually conjectured that the phenomenon that we just described for the 2- and 3-dimensional case actually holds for every dimension. And so Keller's conjecture is that for every n, every tiling of the n-dimensional space with unit cubes, there must be 2 cubes that fully share an n-1 dimensional face. And there have been all kind of cool research on this topic. The first counterexample was found for the 10-dimensional case. And later Mackey found a counterexample for the 8-dimensional case. And recently, we were able to fully solve it. And the answer is here, Keller's conjecture holds for the dimensions 1 to 7, and it doesn't hold for 8 and up. And we were able to do this by making kind of a clever encoding into propositional logic, and then use the machinery that was also used, for example, for Schur number 5 and for the Pythagorean triples. So any questions regarding, say, the kind of more introduction of the
This
part?
is a tangential, but in the problem you just discussed, 8 is special in various ways. So if you know, for example, about the optimal sphere packings, 8 is this particularly simple and pretty dimension. People speculated that there's some connection between that and your 8.
Yeah, no, that's a good question. So no, Tom Hills also mentioned that there are various problems for which the 8th dimension is kind of special. It would be interesting to look into it. So there's now one solution known counterexample for dimension 8. One of the things that we have been considering is also to explore the entire search space, to have all possible counterexamples, to know whether there's just one or one isomorphism class or more multiple.
Yeah.
And maybe also that would help in these kind of questions to see. But yeah, it's interesting that it not only happens for this problem, but for other problems as well, that the 8th dimension is somehow special.
Yeah.
Okay, now let's look at some proofs of unsatisfiability. So when I first, when the paper of the Pythagorean triples got accepted, we put it on archive, and a couple of days later, an editor from Nature contacted me to have an interview. And so I spoke with her for 70 minutes, and I tried to explain to you what I tried to explain to her. What I tried to explain to you is how cool this technology is, and actually that we can really trust it. And so we have linear time speedups, which I think is also pretty cool. But none of this made it in the article. It was only that this proof was 200 terabytes in size, and it was allegedly the biggest math proof ever. I guess especially for this audience that they know that's quite a dubious honor. But I think what it does show is that we can kind of now deal with bigger and bigger problems. And one thing I will want to talk about next is actually that we can have very high trust in these proofs. And let me go into a bit more details here. So first, let's look at this kind of more specifically for the satisfiability problem. So we have a propositional formula or a Boolean formula, and if we give it to a SAT solver and the SAT solver says satisfiable, then this is something that can very easily be checked, right? Does there exist a satisfying assignment? If you give one, you can just linear scan over it, and you know that the solution is correct. But what about the unsatisfiability case, right? So how should we just simply trust them? So these tools have been used for all kind of applications, like in formal verification or in security, and also now in mathematics. And we shouldn't trust them, right? Everybody kind of who wrote code that as soon as you write more than 40 lines, you probably made a mistake somewhere, right? So we really want to make sure that all of this is correct. So what is the idea here? So the SAT solver, in case the formula is unsatisfiable, it produces a proof of unsatisfiability. And so how does this work? So the solver is can do very complicated things, but it needs to transform it into simple steps that a checker can validate. And so all the complicated things are broken down into something much more simple, and a proof checker will actually check everything that it's correct. And ideally, this proof checker is formally verified. Now, before going into details here, let me kind of talk a bit more about the kind of original motivation. So what I already mentioned, these tools might be buggy, and indeed there have been various, all bugs also have been documented, not only in satisfiability, but also in satisfiability modular theories, or in short SMT, or in quantified SAT solvers. And in fact, in the last one, in the beginning, so say a decade ago, these solvers were so buggy that they didn't even talk about bugs, but they just talked about discrepancies. And so they said, okay, the majority of the solvers thinks it's true, and the minority thinks it's false. And so there was no real notion of it, luckily it improved quite a bit, but it kind of shows really that we need some more assurance. Yeah. And so although most of the talk is regarding mathematics, but the tools are used heavily in industry to kind of prove correctness of hardware and software. And we don't want to be in a situation where you say, okay, this hardware is correct, but the correctness claim is due to a bug in the tool that checked it. And so also from industry, there has been quite some kind of request, okay, how can we make sure that the claims that you make are actually correct? And there's also this misconception that, okay, tools might be buggy, but mostly these are the weaker tools. And so the strong tools, they have been used by so many people, and that's kind of, they are correct. But it turns out that from various competitions, winners have been known to be buggy. And what we've seen, especially in the year, say, 2010 to 2015, many of the bugs were actually not implementation bugs or errors, but they were actually conceptual. There were more and more complicated techniques that were added to the solvers, but these techniques were actually unsound. And so one of the things that I've also been promoting is that the proofs are now mandatory. So since 2016 in the SAT competitions, proofs are mandatory. And that really also helped making the tools, at least the results, but also the tools much more reliable. And also especially for this community, right? There's mathematicians, they just don't want to say, okay, a tool said yes or no. They really want to have a justification. Okay, so one alternative that I frequently heard is, okay, but why not just make sure that the solvers are verified? Then that would also solve all the problems. For anybody who really tried to verify such complex tools, they know this is a daunting task. So what I already showed on one of the earlier slides is that, okay, there's been quite some improvements in the solvers every year, and you don't want to verify something which is kind of such a moving piece. And also, it's frequently not clear why a solver is correct. So one of the top tier solvers a couple of years ago was called experimentally correct, which means that it was run on 1 million different instances with a reference solver, and they always gave the same answer, but it turned out that there still was a bug. Although people have been trying it, so trying to verify solvers, and that there is verified implementations of DPLL and CDCL, but what it turns out to be in practice, that solving plus proof logging plus proof verification is way faster than running any of the verified tools. And so there is, of course, some overhead, but the overhead is incomparable to kind of the performance hit that you get when trying to write something formally verified. And one of the advantages of doing the proof logging approach is that you can just have one verified tool. You can really optimize the verified tool, and you can use this for many solvers. Okay, so this was originally the plan, but it was not that everything went smoothly directly. So there were quite some challenges. There were both theoretical and practical in nature. So, for example, some of the theoretical challenges were as follows. Some simple problems, we know that they have exponentially large proofs in the most commonly used proof system, which is called resolution. But tools have been making dedicated techniques to solve these simple problems quickly. Right? What we want is to have a proof which is kind of linear in the size of the solving time. So anything that the solver can do quickly, there should be a short proof. And so we needed to have a proof system that can compactly express all the techniques that are currently in SAT solvers. But there were also various practical things. So one of them was that, okay, how do I implement this proof logging? And how much overhead will this give me? How will the solver be much slower, and will people stop using it? Is it really practical? And how to convince developers to actually support it? Because you can say, okay, I want it, but and I also know from various other competitions that the organizers are reluctant to require it because they say that people will just stop participating. So what we did is, and that I think was kind of an interesting decision, is instead of trying to have the complexity in the solver, what we decided, okay, no, what we're going to do is, okay, as soon as the solver learns something, it tells to the checker, I learned this, and you figure out how I did it. And so we put kind of all the complexity, and so this checker was therefore, it was much more costly, but it was much easier to support. And also we had a reference implementation implemented for the most common code bases for the that were used for the tools. So, and this combination really helped to get early adaptation from the community. And so this is now a reality. So we have kind of arbitrary complex solvers that we have these certificates in strong proof systems, and we don't have to worry about whether the solver is correct or even complete. We just, as soon as the solver returns a certificate of unsatisfiability, we simply check it. And so we can have full confidence in the results. And also what's interesting is that from various developers I've been hearing now, okay, now I am actually much more confident in adding some more complex procedures in the tools because I can now check it. And the nice thing is not only that these the results are just verified, but as soon as there is an error in the proof, the checker says, okay, there's an error and it's exactly there. And it also is a great tool for debugging tools. And so this has now been used not only in the competitions, but also it has been used in industry to check. So if there's claims about correctness of hardware, this is also used to make sure that everything is correct. So this concludes the part about proof of unsatisfiability. Are there any questions?
Yeah, could you say something about what kind of language, or how is it that you can express such a wide variety of proofs for the chapter?
Yeah, so this is, CNF formula, so satisfiability formula is just a set of clauses. And what a proof is simply a sequence of clauses. So so everything in a proof is just you add and delete clauses. So the formula is just growing and shrinking, and that is the only thing that's going on. But the clauses that you can add, they can be quite powerful. So they go beyond resolution. So many of the more complicated proof steps, they can remove solutions, but they guarantee that if there was a solution before adding it, there is a solution after adding it. And so you always preserve satisfiability. And so you can simply with a proof system, yeah, I didn't want to go into too much detail for this talk, but you can just, so for example, by deleting solutions, so you add a clause that removes some solutions, but then there is a technique that you say, okay, if the formula was satisfiable before adding it, then there is a method of satisfying the formula and the clause by doing a specific fix or repair to the assignment that makes it true. And this is actually extremely powerful. And even if you don't use new variables, although that it's allowed, but even if you don't use new variables, then you can have exponentially smaller proofs by using kind of such stronger reasoning.
I see. I get the general idea. Maybe you can send a reference afterwards.
Yeah, I'm happy to set more details. Yes. Any other question? Okay. Now, what's kind of what's in the future? What can we do, and what are the exciting things? Let me first kind of have a brief thing about a meeting that I had with Tim Gowers. So on his blog, he mentioned that he called my proof for the Pythagorean triples the most disgusting proof ever. And so I wanted to have a talk with him what his feeling was about these kind of techniques. And he said he really much liked them, but not the way I use them. And so let me kind of talk a bit about more in detail. So one of the things he would like to have 3 things in the future. So one of them is kind of proof assistant technology. He would really like to see lemmas that a graduate student can work out that can be done automatically. So there are quite some challenges there. Let me not go too much into detail here, but so what he didn't like, and various mathematicians don't like, is that you say there is this enormous proof of whether it's now 200 terabytes or 2 petabytes that doesn't give you any understanding. But he says the very same technology can be used to find counterexamples. He said he expects that about 70% of his time he wastes on things to prove something which is false. Any technology that can quickly give you a counterexample, and ideally, the smallest counterexample, can give you a lot of insight to actually prove something. And so I think this is one of the things that would be cool to kind of for the community to work much more into finding the smallest counterexample. And actually, soon after, so in the next slide, I will talk about a first problem where this can be really helpful. And the other thing is that is proof checking technology. We have that at least for propositional logic. That can be done fully automated, and also one aspect that I didn't mention before is that if the proof that the solvers produce initially was wrong but could be easily fixed, I made the checker in such a way that if there was an easy fix possible, I did automated fixing just to make sure that there was easier adaptation of the technology. And of course, this is also something what you would like more kind of in general, that if you come up with something, but some details are wrong, or some details are missing, how can we kind of fill them in automatically? And for the remainder of the talk, I want to actually focus on 3 classic problems which might be ready for mechanization. And there have been some interesting results initially. So I've been working on all these 3 problems. So the chromatic number of the plane, optimal matrix multiplication, and the collage conjecture. And I think these are exciting problems where automated reasoning can help and potentially actually lead to the solution. Okay, let's first talk about the first problem. So this is the chromatic number of the plane. So we have all points in the 2-dimensional space, and there's only one constraint. If 2 points have exactly distance 1, they must be colored differently, right? So it's very easy to see. And now the question is, what's the fewest number of colors that we can color all the colors in the plane? Now it's very quickly to see, okay, you can of course have 3 points that are all distance 1 from each other, and so you need at least 3 colors. And it doesn't take too much long to actually figure out that you actually need at least 4 colors, because there is this graph called the Motor Spindle, which is shown on the slide, which is a graph consisting of 7 vertices and 11 edges, which has chromatic number 4. So for example, if we would assume it as try to make it with 3 colors, right? If this is a red, yellow, then this yellow and blue, then this also has to be red. And the same holds for deer. This also has to be red. And so there's no way to color this with 3 colors. So there must be at least 4 colors. There's also a nice upper bound of 7 is that if you have this hexagon tiling that you see on the slide, then you can use 7 different color tiles, such that if the outer diameter of the tiles is slightly smaller than 1, so you know that on every tile there are not 2 points with the same color, or they're not with distance 1. And also you can put 2 tiles of the same color far apart from each other, that there are not no 2 points on different tiles with the same color that have distance 1. And so this already shows these bounds were already known in the early 50s, that you need at least 4 colors and at most 7. And many decades went by when lots of people tried to improve things, because the argument is so nice, right? If you look at this, okay, this is such a small, elegant argument. Can we just either make a better tiling to bring down the upper bound, or find a bigger graph that has chromatic number 5 or higher? And the first progress was actually many decades later, which was Aubrey de Grey, who found a lower bound of 5. So he found a graph with 1581 vertices that improved the lower bound to 5. And this breakthrough started a polymath project, and where lots of people tried to improve the results. And I've been doing so as well. So actually, in the first days afterwards, I was able to get this down. And the interesting thing is that I use SAT technology here. So if you give me, say, the graph by de Grey, and what you can do is you can ask the SAT solver, can we color this with 4 colors? And the tool says, no, you cannot color this with 4 colors. But then we have a proof, and you check the proof, and then what you can look at the proof, and they said, okay, but I only use, say, 900 vertices when I trying to check it. So if I only use 900 vertices, then all the vertices that I used are also enough to prove unsatisfiability. And so that's also a graph of chromatic number 5. And if you throw a lot of computation at this problem, then you can get more down and down. So in the weeks afterwards, I was able to get it down to first from in the 800 range, later in the 600 range. And the latest thing I had is the graph shown on the slide, which is 510 vertices. So this is how it looks. Yeah, it might not be, I hope it's a bit clear, but I know Zoom doesn't give you the best resolution. But these are 510 points in the plane, and I give a random 5 coloring of the vertices. So for example, this is distance 1, so between these 2 points. And and this is one of the things that I think SAT solving is an exciting technology, is that not only can give you a counterexample or so a smaller graph with the same property, but yeah, so this is a kind of a first step. Okay, how can we get small counterexamples, and these graphs that I've been able to make might give more insights of how to actually, what makes it to go to chromatic number 5, and maybe we can go to chromatic number 6. Right? And yeah, there have been some cool advances here where the insights by SAT solving are crucial. What are the patterns that actually give us reasonably small graphs?
Let me so the variation. I mean, if you're trying to construct graphs, you might look for graphs that have, some special property or symmetry. So suppose I somehow were looking, doing the same project, but asking that I have some large discrete group symmetry that acts on the graph. Have you thought about that, and how you could encode that? Yeah.
So how I typically do this is I start with a much bigger graph, say sometimes even say 100,000 vertices. And one of the first steps is I try to quickly find, okay, what is it quickly able to refute, to say, okay, there's no 4 coloring. typically the shorter the argument, the shorter the graph. And I do use all kind of symmetries to kind of generate the big graphs. And as you, so it might not be so much clear from the picture, but actually there are quite some symmetries left in this picture.
I see. Okay, that's interesting. Yeah.
Yeah, so I have the papers on this kind of also show more details, but
Right.
they are quite, also the construction of this graph is actually very simple. So we start with a graph with 13 vertices, and we constantly take the Minkowski sum to make it grow, and then that graph has the property. So it's, you just have a base graph of just 13 vertices, which gives you the properties that you want.
All right, interesting. I'll look a bit at this. Thanks.
So another problem which I'm hopeful that automated reasoning might help is matrix multiplication. So we all know how to do this, right? So we have matrix A and B and how to compute the results for C. And if you do this the way you kind of taught it at school, then you use eight multiplications. But the interesting thing is that Strassen tried to prove that you needed at least 8 multiplications, but while trying to prove that, he actually figured out that you can do it with 7. And so the method of doing it by 7 is using 7 multiplications, which are these 7 as shown over here. And so, and then you can fill them in to kind of compute matrix C. And so we now know, and so this actually triggered a lot of research in this direction. And you can not only use this for 2 by 2, but you actually can use it in a general recursive application of n by n matrices to get n to the power log 2 7 operations. And now the question is, can we bring that power down, right? And so let omega be the smallest number such that we can multiply n by n matrices with worst case n to the power omega. And so we know that omega is at least 2 because the matrices have n to the power 2 elements. And of course, we know by Strassen that it is lower than 3. But what's the exact value? So the best value has been improved over time, bit by bit, sometimes with very tiny improvements. And the best results so far are by Allman and Williams, and that is 2.37286. However, Strassen is still the way to go if you want to multiply matrices in practice. So in order to get the low bound, the n must be bigger than the number of particles in the universe. And so Strassen is actually still very interesting because this is actually which works best in practice. Now, the question is, of course, can we improve on Strassen for practice? And so the first case, of course, would be, okay, what's the best open case for the smallest open case, which is 3 by 3? How can we, what's the minimum number of matrix multiplications that we need to multiply to 3 by 3 matrices? And the naive way is n to the cube, right, which is 27. You can easily apply Strassen twice and then get to 25. And the best known upper bound has been by Laderman in 76, which is 23. And although nobody really knows how he did it, so he wrote the paper with the scheme and wrote in the paper that he would write another paper showing, explaining how he did it, but that later paper never materialized. So that's our upper bound, and the best lower bound is 19. In order to beat Strassen, we would need to get down to 21 because the 3 log of 21 is smaller than the 2 log of 7. Now, what is the current state. So the Strassen there actually you can, if you try to construct things, there seem to be multiple ways of doing 2 by 2 with 7 multiplications, but they are all isomorphic. So there's actually only one solution there. And there were 3 other schemes known before we kind of started this research. Using SAT solvers, we have been able to find 13,000 new schemes. And actually, I'm still running things, and so we have now many millions of schemes that we found. But after doing isomorphism checks, it kind of is down to kind of the thousands. And so some of these schemes are actually very exotic, and at least what I've seen in many problems, like for example with say the Schur numbers or other hard combinatorial problems like van der Waerden, typically what you see is up till the point that it's optimal, there's only very few options there. And it seems that at least for matrix multiplication, there is such a broad range of ways to multiply matrices 3 by 3 with 23 multiplications. So I'm still hopeful that actually we can find schemes that they might exist of 22 or smaller, but we haven't found any yet, right? But I think this is also very exciting research how SAT solving might be able to actually find the optimal for kind of small matrices, which might actually be generalized to kind of more for bigger matrices. So this concludes this topic. Any question regarding this?
Yeah, I looked a bit at this work, and and intuitively one can imagine it, using SAT solving by studying, say, the Z2 reduction of the problem. But are there simple ways of using SAT solving that would get more general integer solutions, not easily reducible to Z2?
Yeah, so the interesting thing is that if you you translate, the problem, say you go from integers to booleans and then to Z2.
Yeah.
And then if you find a solution, then actually you can get the solution back to the integers.
Yeah.
So I think in 99% of the schemes that we found, we were able to get to lift them.
Yeah, that's interesting, and I think it kind of says something about the naturalness of this problem. But like other Diophantine problems might not have that property. So if I wanted to do them,
yeah. So I think, of course, it doesn't hold for all problems, right? But this, I think, in cases for which it might be much more rare that you can lift it, right? I think one of the solutions is to just compute a lot of them and then try to lift a single one of them.
Yeah.
But trying to simplify the problem, right? Getting first to the booleans and then to Z2 or maybe Z3, depending on the problem. Yeah. You might be able to get this and then lift things. Yeah.
Oh, yeah. Thanks.
So let me spend the final minutes on the Collatz conjecture. So I can easily talk about this now for 2 hours, but so I just have a few minutes, and let me briefly talk about what this research is. This is together with Scott Aronson and Emre Yulkul. There's also a 50-page paper on this on arXiv for anyone who is more interested in the details. So what's the Collatz conjecture? So given an arbitrary number, if what we're going to apply the Collatz map, which is you divide it by 2 if it's even, and you do it times 3 plus 1 if it's odd. And the question is, if you do this repetitively, will you always reach 1? Right? Now, how are we going to solve this using satisfiability, right? Because this is far from clear. This is a halting problem. Halting problems are undecidable. And how are we going to use this with a tool made for MP problems? So what we're going to do is we're going to find a function, a ranking function, that with non-negative output, such that if you, for an arbitrary number, if you apply the Collatz map on it, then the function value would go down. Since if it would go down, it's never negative. You at some point must reach a zero or some value that you cannot continue. And so for an example, so say if we use the Collatz map for start with 3, we go to 5, 8, 4, 2, and 1. So you can imagine, so can we construct a function that say for 3 returns 5, 5 returns 4, 8 returns 3, 4 returns 2, 2 returns 1, and 1 returns 0. And actually for these small examples, you can easily find such functions using SAT solvers, but how to do this for all the possible numbers. So what we did is the following. So we have 11 rules, and the 11 rules are on the top right. And so what we do, we have 7 symbols. And so in our symbols, the top row is 27, and that is written down, written to 1 in going down, and by constantly applying these 11 rules. And so there's a kind of a highlight also in the lower left. And the only thing that we need to show is that if you apply any of these rules, then things go down. And actually, we don't have to do that strong result. Actually, we actually need to show that if things go down with using one rule, then and for the others everything stays the same, then we can take out that rule, and then we can repeatedly do this, and then that way show termination of the rewrite system. And if we show termination of this rewrite system, this implies Collatz, and the other way around. So if it does not terminate, then Collatz also doesn't reach 1 for all inputs. And so this is what we have been working on. Of course, it might not be realistic to expect this to be successful, but we have some interesting successes so far. So the first success is that, so we have these 11 rules, and if we would have termination of all 11 of them, we prove Collatz. That's maybe too big of a goal, but if we pick any, so we drop one of the rules, any of them, then we have a set of 10 rules, and we can show termination of all these 10, all subsets of 10. So that means that if we somehow were able to eliminate one of the rules, then we actually solve the problem. There have also been various variants being proposed of Collatz. One of them is due to Farkas, and Farkas variant is as follows. So if the number is 1 modulo 3, then we do it -1 divided by 3. Otherwise, so if it's 2 modulo 3 or 0 modulo 3, then we apply Collatz. And Farkas can arbitrary long sequences, but there is, can I say, a page-long mathematical proof that this will terminate. So there's no trivial argument. So it's quite a nice argument how to do this, and our tool is able to come up with some argument that shows termination for this system. And the nice thing is that we also tried it with other tools, and none of the other tools for rewriting was able to do this. So our SAT solving, because we're actually looking for big matrices or in big ranking functions, was able to show this. However, there are also certain problems that we cannot do yet. And the easiest one that we cannot do yet is shown on the slide. And this is the function that if the number is 0 modulo 4, then we do it times 3 divided by 4. If it is 7 modulo 8, we do it times 9 plus 1 divided by 8, and otherwise we terminate. So with So 1/4 we go down, with 1/8 we go slightly up, and otherwise we terminate. So this looks much easier than colons. But nobody can solve this yet. And so we offer a $500 award for anyone who can show termination of this. So if this doesn't terminate, collots doesn't terminate. So it's actually, we took it from collots, but we expect it to terminate, but our tool is not able to show it yet. And apparently this is an easier, but still quite hard problem. So with that challenge, I would like to end the talk. Thanks so much for listening, and I'm happy to answer more questions.
Great, thanks. That's a great talk. Questions from the audience? No question. Okay, there's a question. No, that's a okay.
Sorry, I was just saying I was heading out.
I understand.
Thank you very much. It was a beautiful talk.
Thanks. And nobody needs to be shy.
So Marijn, you've told us so many things that these tools can do. What's the first thing that they can't do? What's the frontier? What's the thing that that maybe one day in the near future we can do, but we can't do now?
So yeah, there are lots of so one of the things that I think, which is still a bit of embarrassing that cannot be done yet, is Ramsey number 4/5. So this was shown in 95 that it is 25, but this is still, SAT solvers cannot produce this. The problem, of course, is that is the symmetries. There is a lot of symmetries in this problem, and I think figuring out how to deal with symmetries would allow us to solve that problem again, and hopefully with a proof. And I'm thinking that if we deal with that problem, then we also can solve other problems for which actually symmetries are the biggest obstacle. So I think dealing with symmetries would allow us to solve some problems for which we know the answer, and hopefully also some problems for which we don't know the answer.
Thanks, Marijn. I'm going to skip off. I have an office hour for our class. So
okay.
Here's a sort of a meta question. So suppose I had a question where I could imagine reformulating it as a stat, or some mathematician might have. And now, how hard a technology is this to use in practice? So I mean, again, like if I look at of course, there's Mathematica for the traditional symbolic algebra. I can at least download Lean and use it. Are the open source SAT solvers really easy enough to use that I could just hope to do it myself, or would I have to collaborate with someone like you, or what is the practical?
Yeah, so that's a good point that you raised. So the tools are actually very easy to download, and they compile everywhere except maybe Windows. But so if you use Linux or Mac, it's just you click make and everything compiles, and it works very smoothly. So the tools have been very well designed. That of course doesn't mean that your favorite problem can be instantly solved by them. And one of the challenges still is that for many problems, figuring out how to write the propositional formula that would solve it, that is sometimes a bit of an art instead of a science. And I've had people come to me, say, okay, I have this problem. I wrote the encoding, and I tried the SAT solver, doesn't work. Can you help me? What is the heuristic I need to use, or something like that? And heuristics might give you 10–20%, but giving a different encoding can typically give you a factor of thousands.
Yeah.
And so although the community is working in this direction to actually, even if you make a poor encoding, to automatically fix it for you, and that everything works out of the box. But too often, for example, if you do something naively, for example, for Keller's conjecture, then the formula is just way too big that even automated repairing is not possible because you cannot store it. And if you do the compact encoding that we had in the paper, then it all becomes easy, right? There, of course, we needed to do with some symmetries, but coming up with a good encoding is unfortunately still sometimes required, and that can make an enormous difference.
Okay. So there's some art to
So,
it.
but if you have a favorite problem, then I'm happy to collaborate.
Okay, well, I mean, I certainly will think about problems that can, that might be suitable. I mean, another kind of a meta question or something maybe you want to comment on. So, of course, there's always this criticism that we get these, totally opaque results that we can't understand, and what do we learn? And then one of the responses would be to say that you have to broaden your concept of understanding. It's true, if the result is just this black 200 terabyte black box, maybe you've only learned one bit of information. But to the extent that the proof has structure, or that you can extract things from it, or you can very quickly solve very similar problems, then you have learned more.
Yeah.
So maybe you could speak to that, examples of things that you could call understanding. I mean, it's implicit in your talk. I think that you did give examples, but.
Yeah, no, so one of the things, for example, so let's talk about, say, the Pythagorean triples problem, right? The 200 terabyte is probably not the shortest proof, but there might not be one that is smaller than a terabyte, right? It's just a highly combinatorial argument, likely, that is the transition point.
Yeah.
However, that doesn't mean that so Moshe Vardi also asked me to look at a much bigger range. So I looked for the numbers 1 to 100,000. And then I was actually able, if you then run it, you get a 1 terabyte proof, right? I think if you're able to go to, say, 10 million, then at some point there will be a short proof, because if you look at the bigger range, right, then there are more refutations and shorter refutations arrive. And so for many of these problems, you can probably have, for the general argument that you cannot color the Pythagorean triples, there might be somewhere, say, in 10 million, 100 million, there might be something short. And it wouldn't surprise me if you just go much further. And these tools can be used for that as well. So I think this is also might be a nice project to see how far can you push it. Because the solving is actually then much quicker, but also how to deal with the big storage of the formula and everything. But yeah, so I think the same tools can be used for understanding, but mostly it's now used for these kind of transition points.
Right.
But that doesn't mean that if you go way beyond these transition points that you can actually
so within the
get some
family of
insights.
problems, some of these problems. So let me throw out another idea, what you said, which is that you might, one might, and for a problem like that, consider some class of random problems, like random sat, or you sample from the integers and so forth. And in that context, there might be some calculation of the average length of a proof, and then you might, if you can do that, you can say, well, if the average length of the proof, for 7,000 integers is a terabyte, then I shouldn't be surprised that for the case of interest, the proof is a terabyte.
Yeah, that might be, but that assumes that the solver will find the shortest proof, right?
Oh yeah, that's right. It might turn out that you found 200 and the average length is 1, and then you have evidence that there is a shorter one.
Yeah, because I'm doing some work here with my PhD student Emre, and so he found a class of problems for which we know there are linear size proofs, resolution proofs, and the solver finds only exponential ones. Right. So although the tools are very strong, right, it doesn't mean that if a short proof exists, that they actually find it, right? Especially if you need to get all elements from over the entire search space, they might not look.
I mean, I could ask the same question I just did in that precise context. I just take one of the standard random SAT problems with uniformly drawn clauses, and now there is some estimate of how big the average proof is, and now I can ask, to what extent does the solver find proofs of that length, right? I mean, you probably do know you have answers to questions like that, right?
Yeah, although, yeah, so an interesting, so for random formulas, actually, so the technology that I mostly use is CDCL here. Actually, on random formulas, it's terrible. So look ahead solvers, I worked on did my PhD on that. They actually are able to get way smaller. So for random formulas, you really do something different than for all these structured instances.
I see, interesting. So that turning that around, of course, the problems you're studying are not random at all. This is a precise.
Yeah. So this the solver. So somehow the conflict-driven closed learning paradigm is able to exploit the structure in problems. Yeah.
Right. Okay.
And that's the reason why we can deal with millions of variables and clauses, because otherwise, of course, this would not be possible, right? You have to exploit structure, otherwise the problem should be much harder, right?
Okay. Right.
Yeah. So this is, I think, the beauty of these technology. This technology is how to get, with some simple rules, exploit structure in big formulas.
Right. More questions? Okay. Well, thanks. This is a wonderful talk, and
Yeah.
thanks again. So we'll be taking a break next week from the seminar series, and on the 27th we'll have Patrick Massot, who will speak about, well, he'll ask the question, why explain mathematics to computers? So about formalization. So I look forward to seeing you all there. Thanks for coming.
Thanks again for the invitation, and thanks for everybody to attend. Bye-bye.
Bye-bye.
Yeah. Great talk. Thanks, Marijn.
Thanks.